If you haven't already watched my video on the conceptual background of double integrals, you can if you want. It might help your understanding if you want to know how iterated integrals form. I'm just going to assume this knowledge here and get right into how to perform triple integration and, more importantly, how to set up a triple integral and its limits. First, let's do some basic examples of triple integration. I'm using MIT's OpenCourseware, specifically the course 18.02 SC if you want to check it out. I'm getting problems from that since it's the course I've been following. I'm going to first show how to do triple integrals, like in a mechanical sense, and then I'll show how to find the limits on a triple integral when you're given a specific shape or domain or region in a 3D space. I feel like that part is a bit more important since triple integrals are pretty much exactly like double integrals computation-wise, except there's another integral to compute. So here's our integral, the triple integral of 2xy squared z dz dx dy. So first begin with the innermost integral and work your way out. So for the first one, we have the integral from 0 to xy of 2xy squared z dz. The variable after d tells you which variable you're going to integrate. So here we're integrating with respect to z, and then x and y are treated as constants. So integrating with respect to z, we get 2xy squared times z squared over 2, and we cancel out the 2 on the top and the 2 on the bottom. Now we evaluate it based on the limits from 0 to xy. We get x times y squared times xy squared, which is x times y squared times x squared times y squared, which then finally becomes x to the third power times y to the fourth power. Moving on to the middle integral, you now take your answer for the first one, which is what we just got, x cubed y to the fourth, and put it in the middle integral. So now we have the integral from 0 to the square root of y of x to the third y to the fourth dx. It's dx since our original order of integration was dzdxdy, so we're just taking the middle differential this time. This means we integrate with respect to x. So treating y as a constant, we now get x to the fourth over 4 times y to the fourth. Then we evaluate it on the limits, from 0 to the square root of y. So now we get the square root of y to the fourth times y to the fourth over 4 minus 0. This becomes y squared times y to the fourth over 4, which is y to the sixth over 4. Finally, the last integral, which is the outmost integral, we will use the last differential. So the outermost integral is the integral from 0 to 2 of what we just got, y to the sixth over 4 dy. This is pretty simple. It only has one variable, and it's like the easiest of the single variable calc integrals you get. After that's evaluated, we get our answer, which is 4.57142. You get the point. Okay, so now let's move on to more difficult examples. So let's do an example from OpenCourseware where it asks us to find the limits on a 3D region in order to find the volume of that shape. So the question is, the rectangular prism having its two bases, the triangle in the yz plane cut out by the two axes and the line y plus z equals 1, and the corresponding triangle in the plane x equals 1, obtained by adding 1 to the x-coordinate of each point in the first triangle.
You want
Supply limits for 3 different orders of integration. Okay, that low-key made no sense, but I think that's because I read it wrong, but I already have everything set up in my OneNote, so don't worry. So yeah, as I said, for convenience, I already drew all this out. Now we'll get to the idea behind the difference in the ordering of the differentials. All of these integrals will yield the same answer ultimately, but the limits will be different, and so will the method kind of. Here's what I mean. If we wanted to integrate dz, dy, dx, we start by picking out a point, any random point on the xy plane, essentially holding both x and y fixed. Then draw out a line in the direction of the variable you're integrating with respect to. In this case, it will be z. So now we have a vertical line poking through the region. You're going to want to evaluate at what z value this ray enters and exits the region. So here, the ray enters the region at z equals 0. Where it leaves is a bit more complicated. It won't leave at the same z value for any two different rays. For example, the black ray leaves at a higher z value than this yellow ray. That's because the top limit of this integral will be a function. The problem stated earlier that the prism is bounded by the line y plus z equals 1. To get this in terms of z, we can rewrite the equation as z equals 1 minus y, after subtracting y from both sides. So now we can see that our z limits go from 0 to 1 minus y. Sometimes limits can be functions in terms of the variables that'll be integrated next. So now for y limits, since we already applied the limits for z, we can ignore the z-axis altogether and just focus on the shadow of the object in the xy plane. I also drew this out. It's just a simple box from 0 to 1 in both x and y directions. We can see that both x and y go from 0 to 1, so those will be our limits. Nothing much more to do there. Now the problem asks us to do the order of integration dx, dz, dy. We'll use the same method. First, pick an arbitrary point on the yz plane to hold y and z fixed, and then increase the ray in the x direction. You'll see that the ray first intersects the region at x equals 0, and last intersects the region at x equals 1. I'm taking the number 1 from the question, by the way. The recreation drawing that I did doesn't show that. So now we know that our limits of x are from 0 to 1. But what about y and z? Well, we can do the same strategy. Ignore the x-axis and just look at the yz plane. We can see that the shadow of the region projected onto the yz plane is a triangle. First, for z limits, we pick a value of y to hold it fixed and increase the ray in the z direction. The ray first hits the triangle when z equals 0, and exits the triangle on the line y plus z equals 1. So to put that in terms of z, that'll be z equals 1 minus y. So z limits are from 0 to 1 minus y. Now finally, y limits. We look at the starting value of y that we can take rays that intersect the region to the end value of y, where rays will stop intersecting the region if we go any further. We see that we first start taking rays at the value y equals 0, and the last ray is at y equals 1. So the y limits are from 0 to 1. I won't do the last part C, because you kind of get the idea by now. I'm just going to move on to spherical coordinates, which is a bit different because of the coordinate system, but still the same idea of triple integration. First, if you'll remember my video on overkill volume of sphere, I used a really stupid method to find the volume of a sphere. That is, I used triple integrals instead of 4 over 3 pi r cubed. It's like trying to kill a housefly with a flamethrower. It's pretty unnecessary, and it makes a 1-second problem into a 3-minute one. But at least I can show you guys the simplest example of spherical coordinates and triple integration, and then we can move on to something harder from OpenCourseWare. So first, I'll go over basic knowledge of spherical coordinates as a refresher. Rho is the distance from the origin to a given point. Also, if a sphere has radius 8, like in this example, and is centered at the origin, that sphere can be described as rho equals 8, because in a sphere all points are equidistant from that center point. Phi is the angle between the z-axis and the point. It can range from 0 to pi. The total range of phi values make up sort of a vertical half circle like a fan or something. Theta can go from 0 to 2 pi, and it's the angle measured from the x-axis. Here's some lecture notes that I wrote on my whiteboard connecting x, y, z, and r to spherical coordinates, derived mostly from trigonometry. Since the cosine of phi is z over rho, we can rewrite that as z equals rho cosine phi. The same idea follows for r. For x and y, we can use their polar definitions and then convert that to spherical by replacing r with rho sine phi. So this is how we'll integrate in spherical coordinates. Usually rho goes first, and then you create a ray stemming from the origin, keeping phi and theta fixed. In the basic sphere example, rho goes from 0 to 8, so those will be our limits. Then hold theta fixed and let phi increase. Again, this forms that kind of fan that I was talking about earlier. Since the fan stretches all the way from the positive z-axis to the negative z-axis, our phi values will be from 0 to pi. So now we have a certain slice of this sphere, but we want the volume of the whole sphere. Theta can give us that. I don't really have a good budget way to visualize this, so you're going to have to use some imagination here, but imagine this fan just sweeping around 360 degrees back to its starting point, filling in the sphere as it goes. So the limits on theta are the values that include all possible fans that intersect the region. So now a more complicated example. The question is asking us to find the limits on this region. The region bounded below by the cone z squared equals x squared plus y squared, and above by the sphere of radius square root 2 and center at origin. I know it says use cylindrical coordinates, but there's a question like right after that says use spherical coordinates, and I have a screenshot of this, so whatever. I drew it out again for convenience, and also what the region looks like if we took it out. Kind of looks like an ice cream cone. First, let's figure out the row limits by the same strategy. Let rho increase while holding theta and phi fixed. This will form a ray. The ray enters the region at rho equals 0 and exits the region at rho equals square root of 2, since the sphere has that radius and is centered at the origin. Row limits are pretty easy in general, but what about phi? We can see that the starting phi value is 0, since we're taking phi starting from the positive z-axis, but the drawing doesn't directly show where phi stops intersecting the region. We'll need to use the given equation of the cone, z squared equals x squared plus y squared, to determine the phi value. I didn't mention this earlier, but a cone can be described just by a value of phi, since the angle between the central axis, which in this case is the positive z-axis, and the outside boundary of the cone is a constant angle. So we can use phi equals constant c to describe some sort of cone. So now we just need to rewrite that equation from the given rectangular coordinates to spherical coordinates. Z squared equals x squared plus y squared becomes z squared equals r squared, since x squared plus y squared is r squared from polar coordinates. And then we just replace z and r with their spherical forms. Rho squared cosine squared phi equals rho squared sine squared phi. Dividing by rho on each side, we get cosine squared phi equals sine squared phi, leading to phi equals pi over 4. Note that the equation cosine squared phi equals sine squared phi can also lead to other values of phi, but we chose pi over 4 since phi ranges from 0 to pi, and it can't be 3 pi over 4 since that would be at the negative z-axis, kind of like here. And when looking at the image, that's not the case. So now, since we want the whole ice cream cone shape, we sweep the fan 360 degrees. Theta limits will be from 0 to 2 pi because of this. And that's pretty much all. If you guys want me to do walkthroughs on other OpenCourseware problems, let me know. Pretty sure I've done all the p-sets, so yeah. See you guys.